Okay, so our first speaker for today is Yuxing Zhou. It's currently a Schmidt AI in Science Fellow at Oxford Chemistry, working on machine learning-driven atomistic simulations of functional materials. So over to you, Yuxing.
Hello everyone. I'm so happy and excited to be here. Thanks for the invitation. I'm going to share with you some of our recent work on machine learning-driven atomistic simulations on memory materials. Well, very recently, I've been to different workshops and seminars and found one topic that is almost impossible to escape. It seems everyone from the big AI companies to new AI startups is in a massive race to find the next generation big thing in materials, for example, new drugs, better batteries, good catalysts, etc. But here's the thing, it's not really just a new AI problem, right? It's a problem how we can understand the material from atomic scale. If you go and grab any computational chemist or a physics and ask them how difficult is it to simulate any given material system at the atomic scale, they're probably going to show you a figure like this. We up here, you got the classic density functional theory, which provides you very close result as compared to the experimental measurement for almost all kinds of complex systems. Well, down here, you have classic empirical potential that's super fast, great for millions of atoms, but you cannot trust them for complex materials and dynamic process. So over the past decade, you have to choose one. Do you want it to be fast or do you want it to be right? But for now, this gap has been bridged by using machine learning into atomic potential. The machine learning task in machine learning potential is very straightforward. We want to regress the potential energy surface so that we can accurately compute the energy and forces of individual atoms for molecular dynamics simulation. We will start from encoding the local environment of our training structure, and then we put them into the machine learning models and train machine learning potential. I might need to skip most of the technical detail here, but the one thing I want to highlight is that machine learning potential have been used in a wide range of research across both academia and industry, from thermodynamic properties for high pressure hydrogen, which is a textbook physics problem, to folding process of protein, which is highly related to a drug design. And in the rest of my talk, I will give you a different example of how machine potential can help to better understanding the memory material from the atomic scale. Throughout my PhD study, I'm particularly interested in a very special material system, the phase change memory materials. A very classic family of the phase change memory materials is located on binary line between the antimatter to right and germanium to right. These GST compositions have already been used in different optical and electrical memory devices. The working principle behind GST is very straightforward. It has two stable phases, the amorphous phase and the crystalline phase. There's a huge electrical contrast between these two phases. So if you take the amorphous phase as the logic 0 and the crystalline phase at logic 1, then GST can storage the binary data 0, 1, 0, 1. These two phases can be switched reversibly and rapidly. In electronic devices, a reset pulse is used to melt it and quench the crystalline phase to form an amorphous phase, and a set pulse can be used to crystallize the amorphous phase back to the crystalline phase. This switching is very, very fast, within tens of nanoseconds or even just picosecond. Density function theory-based molecular dynamics simulation has been a very, very useful tool to understand the fundamental properties of these two phases and their phase transition process. However, as I just mentioned, the optics is too expensive to run. It will become more difficult when we want to simulate a real-world GST device like this, which contains billions of atoms and very complex interface. It will become even more challenging when we consider the realistic programming condition in these devices, especially the non-isothermal condition caused by the Joule heating. This is different from the conventional MPT or MVT simulation where temperature is constant everywhere across the whole cell. Under non-isothermal heating condition, there's a prominent temperature gradient which might give you different structural or dynamical properties. So to enable atomistic simulation of GeTe devices, we developed a chemically transferable machine potential for different GeTe compositions based on the Gaussian approximation potential framework. We call it GeTe GAP22. We hand-built the whole training data set using a interactive training protocol. The most important part of the training data set is the intermediate configuration of melting and crystallization, as I highlight here, which we call then domain-specific configuration. And with the help of this intermediate structure, our potential can more accurately describe the phase transition process. We have performed very comprehensive gradation of our GeTe GAP22 based on a variety of structure analysis across different GeTe compositions. Here, I'll show you the result of RDF and ADF, and you can see they all show very good agreement with the AMD reference. But I think it's more straightforward to compare the same crystallization simulation using GAP and AMD side by side. Please note that here, we use a SOP-based similarity kernel to define the per atom crystallinity. So you will have red colors, which indicate amorphous-like atoms, and yellow atoms represent the crystalline particles. So if I don't tell you which is which, I guess quite hard to distinguish the difference between these two, right? You can also see that the same crystallization simulation now took much less time using gap-driven MD simulation. Now, how do we simulate the non-isothermal heating condition in a device scale simulation? This is the first example of the interactive reset process. To simulate a partial melting process in a mushroom-type device, we manually increase the kinetic energy to the atoms in the programming region on the bottom. The additional kinetic energy has created a prominent temperature gradient across the structure model. And based on the atomic trajectory, we can compute the evolution of the temperature profile during this reset process. And this kind of result can be directly compared to those obtained from a finite element-based method. Using the same protocol, we demonstrate a device-scale simulation of a 50 picosecond reset process in cross-point devices. We use a structural model with the same size of the real-world GeTe cell, which contains more than 500,000 atoms in a box of 40 by 20 by 20 nanometers. We inhomogeneously increase the kinetic energy of the atoms linearly in the vertical direction to mimic a reset heating pulse. So you can see that a gradual melting happens from the bottom to the top of the cell. However, this kind of device scale simulation is still too expensive for GAP, I have to say. That means that GAP potential cannot achieve full cycle device scale simulation, including both reset and set process, because full cycle simulation will require millions of atoms and tens of nanoseconds at the same time. And our solution is to use a different machine and potential framework, which is the atomic cluster expansion framework. ACE is much faster than GAP, but it requires much more data to fit. There are three important steps when we transfer our GAP to ACE. First, we add many domain-specific configurations. Second, we add many small-scale random structure to stabilize the ACE potential. And third, we did hyperparameter optimization, and resulting ACE potential is more than 400 times faster than GAP without losing any accuracy. I still have to skip most of the technical detail here, but there's one thing to note. ACE can make very good use of CPU parallelization. If you happen to have a lot of CPU resources like those provided by RG2, ACE will be a very optimal machine potential for large-scale simulations. Now, with the new ACE potential, we are able to perform the full cycle simulation for the cross-point devices model. It contains a 50 picosecond reset, followed by a 20 nanosecond set and another 70 picosecond reset. And you can see how a single crystal was melted and quenched into amorphous phase and then crystallized back to a polycrystal with different grain size. We can also simulate the full cycle operation for mushroom-type devices, which contains almost 1 million atoms. It's important to note that this ACE potential can capture the stochasticity of nucleation and growth during crystallization, which is the key to understand the realistic switching process in GST devices. Well, by now, I hope you can be somehow convinced that machine potential and large-scale machine learning-driven simulation can do more than you expect to understand the fundamental property of the material. If you want to give it a try, but has no idea of where to start for your own project, don't worry, because I will tell you that people in this field are actively building a good ecosystem. There are two major things from my side I will share today. First, you have to carefully validate the potential before you can fully trust it for any production data. Our group has published a fabulous tutorial for this purpose. The key information here is that the validation is not just about computing numerical errors, as most AI tasks will do. We need to make sure that potential can work as expected in the physical process. A good example of the physically guided validation is the direct comparison of a crystallization simulation between AMD and machine-driven MD, as I just showed in the previous slide. Secondly, nowadays you don't really have to hand build a potential completely from scratch, which might take years, as I did for GST Gap and GST ACE. We have developed a software which automates the training and the benchmarking process. This software is called Autoplex, which is based on random structure search and is jointly developed by our collaborators from Berlin. I will again skip the technical details of how random structure search works in better sampling the structural and chemical space. We have fully released the code and we published the work, which show many examples. Very naively speaking, you only need to plus one button to get your first potential because everything is automated. We show here the automated interactive training process can quickly decrease the numerical error during the training for chemically and structurally complex inorganic systems. More importantly, the automatically generated potential for GST using Autoplex can almost reproduce the same crystallization as I just showed in the previous slide. And please note that this Autoplex generated potential only took 3 days to build. We'll have to stop here, and there's some take-home message for you, as well as links to the papers and codes. Before concluding my talk, I would like to thank my PhD supervisor, Professor Volker Deringer, and all group members from the VLD group at Oxford Chemistry. I also like to thank all our collaborators who have made great contribution to the works.